For centuries, the earliest forms of chemistry were driven by mystical goals, like the pursuit of the philosopher's stone or the elusive elixir of life. But while alchemists chased immortality, practical civilizations were actively mastering the physical world. The ancient Indus Valley used fire to bake bricks and mass-produce pottery, applying chemical transformations at a scale that construction required. Ancient Indian science advanced into specialized fields. In centers like Taxila, they developed complex copper metallurgy, tinted glass, and even utilized early nanotechnology by reducing metals into the fine powders used in Ayurvedic treatments. These cultures manipulated matter through observation and repetition. They could forge metal and glaze pottery with precision, but they lacked an underlying system to explain why materials behaved the way they did. Around 600 BCE, an Indian philosopher named Acharya Khandana moved beyond physical tools to propose a specific theory for the unseen limits of matter. He proposed the existence of the Paramanu, an indestructible, spherical building block of all substances. To Khandana, this was the point where matter could no longer be divided. But how do you prove the existence of a particle that human organs cannot sense? Without a way to measure or classify its properties, the theory remained in the realm of philosophy. Qualitative observation had reached its limit. To map the universe at the atomic scale, humanity needed to invent a systematic language based on strict mathematics. The modern framework for chemistry starts by organizing the visible world. Everything you can touch, drink, or breathe is categorized as a solid, a liquid, or a gas. This visualization shows how those states differ at the particle level. Solids remain vibrating in a grid, liquids stay close but flow past one another, and gases move rapidly through empty space. When substances combine, they form mixtures. They either blend uniformly into a homogeneous mixture, like air, or they separate into uneven zones, like visible clumps of salt and sugar. Elements and compounds differ from these mixtures because they rely on a fixed ratio. A water molecule doesn't vary. It is a permanent bond of 2 hydrogen atoms and 1 oxygen atom. Placing matter into structural categories was only the first step. To test how these structures actually work, scientists needed a universally agreed-upon way to measure their properties. For centuries, scientific data was trapped by geography. A chemist in London using the English system couldn't easily verify the findings of a chemist in Paris using the metric system. That friction led to the Meter Convention of 1875. In a major diplomatic effort, nations gathered in Paris to synchronize global scientific measurements. This created the International System of Units, or SI. It established 7 foundational base units, like the kilogram and the Kelvin, providing the standard alphabet for all scientific data. Standardized definitions allow for crucial distinctions, like the difference between weight and mass. Weight measures gravitational force, which changes based on your location, while mass measures the constant amount of matter inside an object. To keep these standards identical worldwide, the scientific community relied on physical reference objects. This platinum iridium cylinder was sealed under nested glass jars and locked in a French vault to serve as the definition for every kilogram on Earth. The SI units provided the shared tools for measurement, but chemists immediately faced a new problem of scale when they looked toward the atom. Chemistry operates at 2 extremes. Scientists must calculate the bulk yield of an industrial vat alongside the mass of a single hydrogen atom, a fraction of a gram with 23 trailing zeros. Writing out numbers of this magnitude makes standard mathematical operations like addition or multiplication nearly impossible to track. Scientific notation solves this by using exponents. The decimal point shifts, and the long string of zeros collapses into a tween equation that a chemist can actually use. Chemists use significant figures to maintain the integrity of these calculations. These rules require scientists to record the exact level of certainty and the inherent margin of error in every measurement they take. These notations and rounding rules form the operating system required to navigate the atomic scale without losing track of the data. Humanity has moved from the guesswork of early alchemy to a highly exact science of molecular transformation. This precision allows modern chemists to isolate natural compounds and synthesize targeted treatments, such as the cancer drug cisplatin or AZT for HIV. This shared language of measurement is what enables us to engineer superconducting ceramics and develop safer alternatives to the gases that once depleted the ozone layer. Nobel laureate Roald Hoffmann characterized the field as the science of molecules and their transformations. For him, the true power of chemistry lies in the infinite variety of structures we can build from a limited set of elements. The strict math of SI units and scientific notation creates the shared language required for global collaboration. These tools allow us to move past observation and begin manipulating the physical world at an atomic scale.